Let's start with something that should by all rights be impossible. Right now, in the observable universe, there are regions of space that are moving away from us faster than the speed of light. Not almost as fast. Faster. And before you say that can't be right because nothing travels faster than light, you're correct. Nothing travels through space faster than light. But space itself has no such speed limit. Space is not a thing moving through something else. It is the fabric of reality, and it can stretch and expand at any rate the universe sees fit, with no upper bound, no restriction, no apology. And it is stretching right now in every direction at every point simultaneously, pulling the most distant galaxies away from us so fast that the light they emit toward us will never arrive. Those galaxies exist. They are real. They contain stars and possibly planets and possibly things we cannot imagine, and we will never see them, never know them, never reach them, because the universe between us and them is growing faster than light can cross it. There are things that exist that we will never know about. That's not a metaphor. That's physics. And that is where we're starting today, because if that fact doesn't tilt the floor under your feet just slightly, nothing that follows will. This is a video about three things. Things that are scary, things that are extraordinary, and things that nobody, anywhere, at any level of scientific sophistication or technological advancement can currently explain. We're going to spend the next several hours moving through all of them, building a picture of a universe that is simultaneously more violent, more beautiful, more strange, and more vast than anything our daily experience prepares us for. There will be moments in here where the information feels like too much, where the scale becomes genuinely difficult to hold in your mind, where the mysteries feel less like puzzles waiting to be solved and more like walls we may never be able to see past. That's intentional, because the universe does not owe us comprehensibility. It does not scale itself to our comfort level. It simply is what it is, on its own terms, at its own scale, operating by rules that we have only barely begun to understand after thousands of years of trying. So let's go. Let's start with something violent. Somewhere in the observable universe, right now, a star is dying. Not fading gradually, not dimming slowly over billions of years the way our sun will. Dying catastrophically, explosively, in a manner so energetic that the event briefly outshines every other star in its entire galaxy combined. We call this a supernova. And while the word is familiar enough that it might not feel shocking anymore, the reality of what a supernova actually involves should never stop being astonishing. A star is, for most of its life, a battle. It is a continuous, ongoing contest between two forces: the outward pressure of the nuclear fusion happening in its core, where hydrogen atoms are being fused into helium and releasing enormous amounts of energy in the process, and the inward pull of the star's own gravity, which is trying to collapse all that mass into the smallest possible volume. These two forces balance each other for millions or billions of years, depending on the star's mass. The star sits in this equilibrium, burning steadily, held in shape by the tension between expansion and collapse. It is stable only in the sense that a tug of war is stable, two sides pulling in opposite directions with equal force, neither winning, the rope unmoving in the middle. But eventually, for a massive star, the fuel runs out. The hydrogen in the core is exhausted. The star begins fusing helium, then carbon, then oxygen, then silicon. Each successive fuel is more difficult to ignite, releases less energy, burns faster. The star progresses through these fuel stages with increasing urgency, each one buying less and less time. And then it reaches the end of the line: iron. Iron is the ash at the end of the nuclear fusion chain. You can fuse lighter elements together and get energy out. But iron is different. Fusing iron actually absorbs energy rather than releasing it. When the core of a massive star fills with iron, fusion stops. And when fusion stops, the outward pressure that has been holding the star up for millions of years disappears, instantly, completely, without warning. What happens next takes less than a second. The iron core, which can be roughly the size of Earth but contains more mass than the Sun, collapses. In that fraction of a second, it compresses from a sphere roughly 10,000 kilometers across to a sphere roughly 30 kilometers across. The density it reaches is almost incomprehensible. Matter so tightly packed that individual protons and electrons are forced together to form neutrons, creating what is essentially a single enormous atomic nucleus. This is a neutron star, and its formation releases an almost unimaginable amount of gravitational energy, something like 100 times the total energy output of our Sun over its entire 10 billion-year lifetime, released in a fraction of a second. That energy has to go somewhere. It goes outward. It hits the collapsing outer layers of the star, which are still falling inward. And the shockwave from the collision, along with a flood of neutrinos streaming outward from the newly formed neutron star, blasts those outer layers away at a significant fraction of the speed of light. The entire outer structure of the star, everything except that dense core, is expelled in an explosion of such violence that it briefly radiates more light than every other star in a galaxy of hundreds of billions of stars put together. A single dying star, brighter than an entire galaxy. That is what a supernova is. The remnant left behind is extraordinary. The neutron star at the center. If the original star was massive enough, this becomes a black hole instead. But let's start with the neutron star. Is one of the most extreme objects in the known universe. It is roughly 20 to 30 kilometers in diameter, smaller than most cities. The island of Manhattan is longer than some neutron stars are wide. And yet a single teaspoon of neutron star material would weigh approximately 1 billion tons. Take a moment with that. A teaspoon, 1 billion tons. If you could somehow bring a teaspoon of neutron star material to Earth and set it on the surface, it would immediately sink through the crust, through the mantle, through the outer core, and come to rest somewhere in the inner core. The Earth's surface material cannot support it. A teaspoon of neutron star would fall through our planet like a bullet through paper. And these objects spin. They spin fast, some of them extraordinarily fast. When the original star collapsed, its rotation sped up dramatically through the conservation of angular momentum, the same physics that causes a figure skater to spin faster when they pull their arms in. A neutron star that has collapsed from a stellar core spinning once every several days now completes full rotations hundreds of times per second. Some neutron stars, called millisecond pulsars, rotate more than 700 times per second. 700 full rotations of an object the size of a city in a single second. These objects are spinning so fast that their surfaces are moving at a significant fraction of the speed of light. And as they spin, if they have the right magnetic field geometry, they emit beams of radio waves from their magnetic poles that sweep across space like a cosmic lighthouse. We detect these as pulses of radio waves arriving with extraordinary regularity. So regular that when the first pulsar was detected in 1967, astronomers initially labeled it LGM-1, where LGM stood for Little Green Men, because no natural phenomenon they knew of could produce pulses of radio waves with such clockwork precision. It took months of analysis before they convinced themselves it was a natural object and not some kind of alien signal. That's how precisely pulsars keep time. Some of them are more accurate than the best atomic clocks on Earth. Now let's go further. Let's talk about what happens when a star collapses and doesn't leave a neutron star but something else entirely. When the original star is massive enough, roughly more than about 25 times the mass of our Sun, the neutron star itself isn't stable. The mass is too great, the gravity too strong, for even neutron degeneracy pressure to halt the collapse. The neutron star continues to compress, and it keeps compressing, and there is nothing left in the known universe capable of stopping it. It collapses into a mathematical singularity, a point of zero volume and infinite density, and it creates around itself a region of spacetime so curved that not even light can escape. A black hole. The boundary of this region is called the event horizon, and it is simultaneously one of the most studied and most misunderstood objects in all of physics. The event horizon is not a surface. It is not a wall. It is not something you would see or feel or interact with if you crossed it. It is simply a threshold, a point of no return, defined by the geometry of spacetime in the vicinity of an extreme mass. From outside the event horizon, a black hole looks dark because no light escapes from within it. But the darkness itself is not uniform, and it is not simple. The gravitational field around a black hole warps the paths of light rays from background stars and galaxies, creating a visual effect called gravitational lensing, a halo of distorted, brightened starlight surrounding the dark central region. When scientists photographed a black hole for the first time in 2019, capturing an image of the supermassive black hole at the center of the galaxy M87, what they saw was exactly this: a ring of glowing gas, brightened and distorted by the extreme curvature of spacetime, surrounding a dark central shadow. It looked like nothing so much as a gateway, an eye in the darkness. The fact that we can look at an image of a black hole, an object whose very existence challenges the limits of our physical theories, and feel like we're recognizing something, like we're seeing something almost familiar in its shape, is one of the stranger aesthetic experiences that modern astronomy has produced. Black holes come in a range of sizes that spans many orders of magnitude. Stellar mass black holes, formed from the collapse of individual stars, range from a few times to perhaps 100 times the mass of our Sun. Intermediate mass black holes, which are theoretically predicted but observationally rare, range from thousands to tens of thousands of solar masses. And then there are the ones at the centers of galaxies, the supermassive black holes, ranging from millions to billions of solar masses. The one at the center of M87, the first one ever photographed, has a mass of approximately 6.5 billion solar masses. Its event horizon is so large that our entire solar system could fit inside it many times over. And the one at the center of our own Milky Way, called Sagittarius A star, has a mass of about 4 million solar masses and an event horizon roughly 40 times the diameter of the Sun. Why does every large galaxy appear to have a supermassive black hole at its center? We don't fully know. The relationship between galaxies and their central black holes is one of the most active research areas in astrophysics. What we do know is that there appears to be a tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, its size, the speed of its star's orbits, the structure of its bulge. This correlation is so tight, so consistent across galaxies of wildly different types and sizes, that it suggests the galaxy and its black hole somehow grew together, each influencing the other's development over billions of years. The black hole didn't just appear in the middle of a pre-existing galaxy. It is, in some deep sense, part of what the galaxy is. The two are intertwined in their formation and their history in ways we are only beginning to map out. And these supermassive black holes are not always quiet. When they are actively feeding, when gas and dust and stars are falling into them in large quantities, they become the most luminous objects in the observable universe. We call these active galactic nuclei, and the most extreme version of them are called quasars. A quasar is a supermassive black hole eating so much material so fast that the infalling gas forms a superheated accretion disk around it, and that disk radiates so much energy that the quasar outshines its entire host galaxy by a factor of thousands to hundreds of thousands. The brightest quasars are roughly 1 trillion times more luminous than our Sun. They are visible from billions of light years away, their light reaching us after journeys that began billions of years before the Earth existed. When we observe quasars, we are looking deep into the past of the universe, back to an era when black holes were feeding voraciously and the universe was much younger and much more violent than it is today. But even quasars are not the most energetic events we know of. That title belongs to something we discovered almost by accident, and which remains, decades after its discovery, one of the most mysterious and awe-inspiring phenomena in the universe. Gamma-ray bursts, brief, intense flashes of gamma radiation that arrive without warning from random directions in the sky, release more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. Let that go through you slowly. The Sun, over 10 billion years, and a gamma-ray burst releases the equivalent in seconds. Some gamma-ray bursts last for milliseconds. Some last for hours. The shortest ones appear to be caused by the collision of two neutron stars, or a neutron star and a black hole, spiraling together under their mutual gravity until they merge in a cataclysmic collision. The longer ones appear to be associated with the most extreme versions of the stellar collapse we discussed earlier. Massive stars dying so violently that they produce a narrow jet of material, moving at nearly the speed of light. And it's this jet that creates the gamma-ray burst when it breaks through the surface of the star and plows into the surrounding gas. If a gamma-ray burst were aimed at Earth from within a few thousand light-years, the gamma radiation would strip our ozone layer and expose the surface to levels of ultraviolet radiation that would make the planet essentially uninhabitable within months. This is not purely hypothetical. Some scientists have proposed that one or more of the mass extinction events in Earth's history might have been triggered by a nearby gamma-ray burst. There's circumstantial evidence, suggestive but not conclusive, that the Ordovician mass extinction, which happened about 445 million years ago and wiped out roughly 85% of all marine species, might have been caused by a gamma-ray burst within our galaxy. We can't prove it, but we can't rule it out. And the fact that the most energetic events in the universe are also aimed from time to time in our direction, that the universe occasionally fires these continent-sterilizing blasts of radiation and they go off in random directions, sometimes pointing at galaxies like ours, is the kind of fact that the universe offers with complete indifference to how it makes us feel. Now let's slow down from the violence for a moment and talk about something that seems quieter but is, in its own way, just as unsettling. Let's talk about dark matter. You can't see it. You can't touch it. You can't detect it directly with any instrument we've ever built. And yet it makes up roughly 27% of the total energy content of the universe, compared to ordinary matter. All the atoms, all the molecules, everything you have ever seen or touched or eaten or breathed or been, which makes up only about 5%. Dark matter outweighs everything we can see by more than 5 to 1. It is the dominant form of matter in the universe, and we have absolutely no idea what it is. We know it exists because of its gravitational effects. When astronomers look at how galaxies rotate, they find something deeply wrong. The stars in the outer regions of galaxies orbit their galactic centers far too fast. According to the math, if a galaxy contained only the visible matter we can see, the stars, the gas, the dust, the outer stars would be moving so fast that they'd fly off into intergalactic space. They'd escape the galaxy entirely. But they don't. They stay in their orbits, rotating around the galactic center at speeds that only make sense if there's a massive invisible structure, a halo of dark matter surrounding the galaxy and providing the extra gravitational glue to hold everything together. Every galaxy we have ever studied shows this effect. Every one, without exception. The entire observable universe is wrapped in a framework of invisible matter that we cannot see and have never directly detected. The leading theoretical candidates for what dark matter is made of are various exotic particles that don't appear in the standard model of particle physics. Particles that interact with ordinary matter only through gravity and possibly through the weak nuclear force, which is why they're impossible to see with telescopes and extraordinarily difficult to detect even in experiments specifically designed for the purpose. Experiments buried deep underground, surrounded by hundreds of meters of rock to shield them from cosmic rays, cooled to temperatures near absolute zero to reduce thermal noise, have been searching for dark matter particles for decades. The most sensitive of these detectors has never seen a single confirmed dark matter event. Either dark matter particles are far rarer or far less interactive than the simplest models predict, or there's something fundamentally different from any particle we've theorized, or there is something wrong with our understanding of gravity itself. That last possibility is taken seriously by a significant minority of physicists. Modified gravity theories. Attempts to revise Einstein's equations in ways that would explain galaxy rotation curves without invoking invisible matter have had some successes and some failures over the decades. The most popular of these, called MOND or Modified Newtonian Dynamics, correctly predicts the rotation curves of many individual galaxies, but it struggles to explain the behavior of galaxy clusters and the large-scale structure of the universe, where dark matter models do much better. We seem to need dark matter for some phenomena and modified gravity for others, which suggests that neither theory is completely right, and that the true answer is something we haven't found yet. Here's a detail about dark matter that I find particularly unsettling. Dark matter doesn't just surround galaxies from the outside, it's inside them too. It's inside the Milky Way, and it's inside our solar system, and it's inside this room, right now, wherever you are. You are, at this very moment, surrounded by dark matter particles moving through your body, and through the walls, and through the earth beneath you with no interaction whatsoever, not slowing down, not deflecting, not registering in any way. The planet you're standing on is essentially transparent to dark matter. It passes through everything as if everything else doesn't exist, because to dark matter, in a real sense, everything else doesn't exist. You and the entire world you live in are made of a type of matter that constitutes a tiny minority of the total matter in the universe, and the dominant type of matter flows through you without the faintest acknowledgement of your existence every second of every day. And if dark matter is strange, what comes next is stranger still, because dark matter at least interacts gravitationally. At least it obeys the rules we understand. Dark energy doesn't even do that in any comfortable way. Dark energy is the term we use for whatever is causing the accelerating expansion of the universe, and it makes up roughly 68% of the total energy content of everything. Between dark matter and dark energy, the universe we can see and study, all the atoms, all the molecules, all the stars and planets and galaxies and nebulae and comets and black holes, constitutes approximately 5% of what exists. We live in a universe where 95% of what's there is completely unknown to us. We don't know what it is, where it comes from, why it exists, or what it will ultimately do. We know it's there because the universe behaves the way it does, and we have given it names: dark matter, dark energy, that tell you nothing except that it doesn't glow and we don't understand it. Dark energy was discovered in 1998 when two independent teams of astronomers, each studying a particular type of supernova that can be used as a cosmic distance marker, found that distant supernovae were dimmer than they should have been if the universe were expanding at a constant rate. Dimmer means farther away. Farther away means the universe had expanded more than expected between then and now, and more expansion than expected means the expansion is accelerating. Something is pushing the universe apart faster and faster over time, rather than letting gravity gradually slow the expansion down. The discovery was so unexpected, so contrary to every model anyone had been working with, that the teams checked their data repeatedly before announcing it. It earned its discoverers the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of the universe's fate. Because if the expansion is accelerating, what does that mean for the long-term future? It means that over the next billions of years, galaxies that are currently visible to us will gradually redshift beyond detectability as they move away faster and faster. It means that 1 trillion years from now, the Milky Way and its closest gravitationally bound companions will be all that's left visible to any civilization that might exist. The rest of the observable universe having been carried beyond the cosmological event horizon, the universe will look completely empty except for the local gravitational neighborhood. Any civilization that arises after that point will look out at the sky and see almost nothing, and they may conclude that their little island of galaxies is all there is. They will have no way of knowing that they inhabit a tiny remnant of what was once a vast galaxy-filled cosmos. They will look out and see only darkness, and they will be right to conclude that nothing is out there, even though the truth is that the universe is full of galaxies they will never see, moving away from them faster than light in every direction. That is the future that dark energy is building. A universe that gradually erases its own history from the view of any observer within it. A universe that becomes progressively more empty, more isolated, more dark, as the accelerating expansion carries the evidence of its past beyond the reach of anyone who might want to study it. Let's take a turn now towards something that starts in the realm of the strange and beautiful and ends somewhere genuinely unsettling. Let's talk about time. We experience time as a flow. We experience it as directional. It moves from past to future, never the other way around. You remember yesterday and not tomorrow. Causes precede effects. Things age and decay rather than becoming younger and more organized. This directionality of time, what physicists call the arrow of time, feels so fundamental to our experience of reality that it seems like it couldn't possibly be anything other than an absolute feature of the universe. And yet, at the fundamental level of physics, the laws that govern the behavior of matter and energy are almost completely symmetric in time. The equations of quantum mechanics, of classical mechanics, of electromagnetism, run them forward and they describe particles and fields behaving one way. Run them backward in time and they describe particles and fields behaving in ways that are mathematically equally valid. The laws of physics, at their deepest level, don't distinguish between the past and the future. So why does the universe have an arrow of time? Why do we experience time as going in one direction? The most accepted answer connects back to entropy, the tendency of systems to move from ordered low-entropy states to disordered high-entropy states. Drop a glass and it shatters. Run the video backward and you see the shards jumping up and reassembling into a glass, which looks deeply wrong because it is deeply improbable. Not impossible. Nothing in the laws of physics forbids it, just so astronomically unlikely that it never happens. The universe moves from lower entropy to higher entropy not because it's required to by any fundamental law, but because the number of high-entropy states so vastly outnumbers the number of low-entropy states that random processes inevitably move things toward the more disordered configurations. But this raises a profound question. If the universe tends naturally toward higher entropy, why does it start from a low-entropy state? Why was the early universe, immediately after the Big Bang, in such an extraordinarily ordered low-entropy configuration? Why didn't it just start out already maximally disordered? That question doesn't have a fully satisfying answer. The Big Bang appears to have produced a universe in an extremely low-entropy state, and that initial low entropy is the ultimate source of the arrow of time, the reason time goes in the direction it does, the reason we remember the past and not the future, the reason effects follow causes. But why the Big Bang produced that low-entropy initial condition is one of the deepest unsolved problems in cosmology. Some physicists have proposed that there was something before the Big Bang, a previous phase of the universe perhaps, or a different kind of process, that set up those initial conditions. But we have no observational evidence of anything before the Big Bang, and our current theories break down precisely at the moment of the Big Bang itself, leaving us unable to extrapolate backward through it. Now let's talk about light in a way that most people haven't thought about. When you look at the night sky, you are looking at history. The light from the moon left its surface about 1.3 seconds ago. The light from the sun left it about 8 minutes ago. The light from the nearest star other than the sun left it about 4.25 years ago. You're not seeing the night sky as it is, you're seeing it as it was, with every object at a different depth in time, a layered archive of the universe's past. When astronomers observe very distant galaxies billions of light years away, they're looking at those galaxies as they were billions of years ago, in some cases when the universe was only a fraction of its current age. The universe's past is written across the sky, if you know how to read it. The most distant light we can detect comes from the cosmic microwave background, a faint, nearly uniform glow of microwave radiation that permeates the entire sky in every direction. This is the afterglow of the Big Bang itself, the radiation that was emitted when the universe was about 380,000 years old and had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was too hot and too dense for light to travel freely. It was immediately reabsorbed by the dense plasma. The moment atoms formed, the universe became transparent, and the light that was trapped in that hot plasma was released and has been traveling ever since. We detect it today as microwaves because it has been so dramatically redshifted by the expansion of the universe over the subsequent 13.8 billion years. This radiation carries information about the state of the universe at 380,000 years old, and from studying its tiny temperature variations, fluctuations of about 1 part in 100,000, cosmologists have been able to learn an enormous amount about the structure, composition, and history of the cosmos. But 380,000 years after the Big Bang is the earliest we can see directly. What happened before that, before the universe became transparent, is beyond the reach of any telescope that detects light. To see further back, we need different messengers. Neutrinos, ghostly, nearly massless particles that interact only through the weak nuclear force and gravity, decoupled from the rest of the universe when it was about 1 second old, and the universe should be filled with a cosmic neutrino background analogous to the cosmic microwave background but from much earlier. We have never detected it directly because neutrinos from that era have such low energies that no current instrument is sensitive enough, and gravitational waves, ripples in spacetime produced by the earliest moments of the Big Bang, possibly from inflation, could in principle carry information from the very first fractions of a second after the Big Bang. Detecting them would be like hearing the universe's first heartbeat. Let's talk about inflation because it's one of the most remarkable and strange ideas in all of modern cosmology, and it's one that most people have never heard explained in a way that makes clear how genuinely extraordinary its implications are. The Big Bang model, in its simplest form, has several observational puzzles that it cannot explain without additional ingredients. One is called the flatness problem. Why is the geometry of the universe so extremely close to flat? The universe could, in principle, be highly curved, like the surface of a sphere or like a saddle. But observations consistently show that it's flat to extraordinary precision. For the universe to be this flat today, the conditions at the Big Bang would have had to be fine-tuned to an almost incomprehensible degree of precision. Another puzzle is called the horizon problem. Why is the cosmic microwave background so uniform in temperature across the entire sky? Regions of the sky that are opposite each other, separated by distances so large that they could never have been in causal contact in the standard Big Bang model, have temperatures that match to 1 part in 100,000. How did they know to be the same temperature if they've never interacted? The answer proposed in 1980 by physicist Alan Guth is inflation, a period of extraordinarily rapid, exponential expansion in the first tiny fraction of a second after the Big Bang, during which the universe grew by a factor of at least 10 to the 26th power, possibly far more, in something like 10 to the minus 32 seconds. This is expansion so fast that it makes the current accelerating expansion of the universe look like it's standing still, and it elegantly solves both problems. The flatness is explained because inflation stretches any initial curvature of the universe so dramatically that it appears flat, the same way the surface of a balloon looks flat when the balloon is inflated to enormous size. The horizon problem is solved because the regions of the sky that appear causally disconnected were actually in contact before inflation blew them apart. They reached thermal equilibrium in the tiny fraction of a second before inflation began, and then inflation separated them so fast that they've had no subsequent contact. But inflation has a consequence that goes far beyond solving observational puzzles, and it's a consequence that some physicists find thrilling and others find deeply uncomfortable. If inflation happened, it almost certainly didn't happen uniformly. Quantum fluctuations during inflation would have caused different regions to inflate by different amounts, and in many versions of inflation theory, some of those regions would have inflated so much that they effectively became separate universes, causally disconnected from ours, with their own physical histories, and possibly even their own laws of physics and constants of nature. This is the inflationary multiverse, and if it is real, our universe is one of an essentially infinite number of bubble universes, each one born from its own inflationary event, each one expanding and evolving in its own way, none of them accessible to any of the others. The multiverse is philosophically uncomfortable for many scientists because it may be fundamentally untestable. If other universes are causally disconnected from ours, we can never observe them directly. Any prediction that relies on what's happening in other universes is a prediction we can't verify. Some physicists argue that this makes the multiverse not science but metaphysics, a theoretical construct that explains everything because it can accommodate any observation, which means it explains nothing. Others argue that the multiverse is a legitimate scientific hypothesis because it follows logically from well-tested theoretical frameworks, even if its direct predictions are currently beyond our experimental reach. The debate is ongoing, and it touches on deep questions about what science is, what counts as an explanation, and what we mean when we say we understand something. Let's come back to things we can observe because there are mysteries enough in the parts of the universe we can actually see. Let's talk about fast radio bursts. In 2007, astronomers sifting through archival data from a radio telescope in Australia found something unexpected. A single, intense burst of radio waves that had occurred in 2001 but had never been noticed. It was extraordinarily brief, lasting only a few milliseconds, but in that brief burst it released as much energy as the sun emits over days or weeks, and its signal bore the characteristic signature of having traveled through a vast amount of intergalactic medium, the thin gas that fills the spaces between galaxies, suggesting it had come from a source billions of light-years away. This was the first detected fast radio burst, and it was initially treated with skepticism. A signal that lasted only milliseconds and had been found in archival data could have been a terrestrial radio frequency interference event, a microwave oven someone opened at the wrong moment, or a cell phone near the telescope. But then more bursts were found, and then more, and then some of them were found to repeat. The same source emitting multiple bursts separated by days or weeks or months. The repeating bursts definitively ruled out any one-time catastrophic event as the source of all fast radio bursts, since you can't have a one-time catastrophe that happens multiple times. And the sheer number of fast radio bursts being detected, thousands now, with the most sensitive telescopes estimating that something like thousands of them occur every day across the observable universe, made the idea that they were all instrumental artifacts completely untenable. We now have reasonably good evidence that at least some fast radio bursts come from magnetars, neutron stars with extraordinarily strong magnetic fields, among the strongest known in the universe. A magnetar in our own galaxy produced a fast radio burst in 2020 that was detected by multiple telescopes, providing the first confirmed source for at least one class of these events. But whether all fast radio bursts come from magnetars, or whether there are multiple types of sources, or whether some of them come from something completely different that we haven't yet identified, these questions are still open, and the ones that repeat, with the complex patterns and subburst structures some of them show, suggest that the physics behind them may be richer and stranger than the simple magnetar model captures. Now let's talk about something that has no explanation at all. Something that has been studied for decades and remains as mysterious as the day it was discovered. The anomalous signals from the WOW signal. On August 15, 1977, a radio telescope at Ohio State University was conducting a sky survey as part of the search for extraterrestrial intelligence when it recorded a strong, narrowband radio signal that bore exactly the characteristics that SETI researchers had predicted an extraterrestrial signal might have. The signal lasted exactly 72 seconds, the maximum duration that the telescope could observe any point in the sky as Earth's rotation carried the beam away, and its intensity varied in the smooth, bell-curve shape expected from a real astrophysical source. Astronomer Jerry Amen, reviewing the computer printout several days later, was so struck by the signal that he circled it and wrote "wow" in the margin. The name stuck. The "wow" signal has never been explained and has never been detected again. It came from the direction of the constellation Sagittarius, from a region of sky that contains no known stars or other radio sources that could plausibly have produced it. Its frequency was close to the 1420 MHz hydrogen line, the frequency of radio emission from neutral hydrogen, which SETI researchers have long argued would be a natural choice for any intelligent civilization attempting interstellar communication, since hydrogen is the most abundant element in the universe and any technological civilization would know about it. Its signal strength, if it came from an extraterrestrial source, implied a transmitter of enormous power, far beyond anything we could currently build. Every attempt to re-observe the signal has failed. In 2016, a group of researchers proposed that the signal might have been caused by a pair of comets passing through the field of view of the telescope and emitting radio waves through an interaction with the solar wind. This explanation is broadly consistent with the signal's properties and was taken seriously by some researchers. But it's contested. Not everyone agrees that comets could produce a signal with those characteristics, and the question of what the "wow" signal was remains genuinely, officially open. Let's pivot now to something closer to home. And by closer I mean still incomprehensibly far, but at least within our own solar system. Let's talk about Oumuamua. In October 2017, astronomers using a telescope in Hawaii detected a small object moving through the solar system on a trajectory that was unmistakably hyperbolic. It was not orbiting the sun. It was passing through the solar system on a path that had brought it from outside and would carry it back out, never to return. This was the first confirmed interstellar object ever detected. The first thing we'd found that had come from another star system and was just passing through. They named it Oumuamua, from Hawaiian words roughly meaning first distant messenger. What they found when they studied it was deeply strange. Its brightness varied dramatically as it tumbled through space, suggesting an unusually elongated or flattened shape, perhaps 10 times as long as it was wide, like a cigar or a thin disk. This is unlike any solar system object we've ever observed. Comets and asteroids, even elongated ones, aren't that extreme in their proportions. But stranger still was its trajectory. As it moved away from the sun, its speed didn't follow the trajectory you'd expect from a purely gravitational path. It was accelerating. Not by much, but measurably. The standard explanation for this kind of non-gravitational acceleration in a small body is outgassing. When a comet gets close to the sun, the ice and volatile materials in it vaporize and create jets of gas that push the comet slightly off course and add a small velocity component to its motion. But astronomers looked for evidence of outgassing in their observations of Oumuamua and found none. No coma, no tail, no detectable gas or dust being emitted. Whatever was causing the acceleration, it wasn't outgassing, at least not of any type we've previously observed. Harvard astronomer Avi Loeb caused a significant controversy when he published a paper suggesting that the non-gravitational acceleration could be explained if Oumuamua were a thin, flat object being pushed by the pressure of sunlight, essentially a light sail, an object deliberately designed to be propelled by radiation pressure, of the type that some engineers have proposed for future spacecraft. Loeb argued that the natural explanations had problems and that an artificial origin could not be ruled out. The vast majority of the scientific community disagrees with this interpretation and believes that Oumuamua was almost certainly a natural object, even if its properties are unusual and not fully understood. But the fact that we can't fully explain what Oumuamua was, where exactly it came from, and what caused its anomalous acceleration, that's not in dispute. It remains one of the most peculiar objects ever observed in our solar system. And Oumuamua is not the only strange thing happening in our solar system. There's a hypothesis that has been circulating in the planetary science community for about a decade that our solar system contains a ninth planet. Not the dwarf planet Pluto, which was famously reclassified, but a genuine large planet, possibly several times the mass of Earth or even larger, orbiting in the distant outer solar system in a highly elongated orbit that keeps it far from the sun for most of its year. The evidence for this hypothetical Planet 9 comes from the orbits of a group of small, distant solar system objects called trans-Neptunian objects, or TNOs. Several of these objects have orbits that are clustered in a way that appears to be statistically significant. They seem to be aligned in a pattern that's unlikely to be random, and the most natural explanation for this alignment is the gravitational influence of a large unseen body far out in the solar system. Planet 9 has not been found. Extensive searches of the sky have turned up nothing in the regions where it might plausibly be. Either the orbital clustering is a statistical artifact, a coincidence in a small sample of objects that will disappear as more TNOs are discovered, or Planet 9 is there but we haven't looked in the right place yet, or there is some other explanation for the clustering that doesn't involve an undiscovered planet. Each of these possibilities is being actively investigated. If Planet 9 does exist and is eventually found, it would be one of the major discoveries in solar system science in recent decades. If it doesn't, and the apparent clustering of TNO orbits turns out to be a fluke, then the mystery of why several distant solar system objects have aligned orbits will need a different answer. Let's talk about some of the universe's most extraordinary objects. Things that exist and behave in ways that seem to violate intuition at every turn. Let's talk about neutron stars more deeply, because we skated over some of the most extraordinary things about them. The surface of a neutron star is not like the surface of any other object you can conceptualize. The crust, the outermost solid layer of the neutron star, is composed of atomic nuclei arranged in a crystal lattice, but at densities millions of times higher than anything found on Earth. The nuclei themselves are distorted by the extreme pressure, becoming elongated and then merging together into structures called nuclear pasta, a series of phases of nuclear matter named after their shapes, from gnocchi-like spheres to spaghetti-like cylinders to lasagna-like sheets, depending on the density. Nuclear pasta is theoretically the strongest material in the universe, roughly 10 billion times stronger than steel. Nothing we have ever made or ever will make comes close to approaching its strength. The magnetic fields of some neutron stars, the magnetars, are the strongest known in the universe. A typical neutron star has a magnetic field around 1 trillion times stronger than Earth's. Magnetars have fields that are 1,000 times stronger still, roughly 10 to the 15th Gauss. To put that in some perspective, a magnetic field of just 10 Gauss is enough to visibly deflect a compass needle. 50,000 Gauss is enough to rip metallic objects toward a magnet with violent force. A magnetar's surface field is 10 to the 15th Gauss. If a magnetar were placed where the moon currently is, the electromagnetic effects would be lethal at Earth's surface and would disrupt the electronics of everything ever built by human civilization. The field would pull the iron from your blood. It would affect the quantum states of atoms in your body at a distance of 300,000 kilometers. Magnetars occasionally produce what are called starquakes, events where the crust of the neutron star abruptly adjusts, shifting by perhaps a millimeter, in response to the enormous stresses placed on it by the magnetic field. A millimeter. On a neutron star, a shift of 1 millimeter in the crust releases more energy than our sun emits in years, in a fraction of a second, as an intense burst of X-rays and gamma rays that can be detected from tens of thousands of light-years away. In 2004, a magnetar called SGR 180620 produced a giant flare that for about 0.2 seconds was the brightest event ever recorded from beyond our solar system. It was 50,000 light-years away. If it had been 10 light-years away, the energy it deposited in Earth's upper atmosphere would have been comparable to a nuclear bomb exploding in the sky. A magnetar 50,000 light-years away, almost on the other side of the galaxy, and it would have been comparable to a nuclear bomb if it were just 10 light-years away. From magnetars, let's go to something even more exotic. Theoretically predicted but never confirmed. What if two neutron stars merge, but the mass of the merger product isn't quite enough to form a black hole? What if it forms something in between, denser than a neutron star, but not so dense that light can't escape? Some physicists have theorized the existence of objects called quark stars, neutron stars compressed beyond the point where neutrons can hold their structure, causing them to dissolve into their constituent quarks. Quarks are the fundamental particles that protons and neutrons are made of, and in a quark star, instead of a lattice of neutrons, you'd have a dense sea of free quarks, up quarks, down quarks, and possibly strange quarks, in a phase of matter that has no analog in our everyday experience. Some theoretical models suggest that quark stars could be stable and might exist in nature. A few candidate objects have been identified: neutron stars with properties that are difficult to explain in standard models and that might be consistent with quark star properties. But no quark star has been definitively confirmed, and the physics of quark matter at these densities is far from fully understood. Going further still, some physicists have speculated about even more exotic objects: strange stars composed entirely of strange quark matter. Boson stars made not of fermions like neutrons and quarks, but of bosonic fields. Preon stars, in which even quarks have dissolved into hypothetical subparticles. Gravistar, which propose replacing the black hole singularity with an exotic vacuum energy core. These are not mainstream physics, but they are not dismissed either. They represent the outer edge of our theoretical understanding, places where our equations work, but where we have no experimental data to guide us. Whether any of these exotic objects exist in nature is genuinely unknown. Let's talk about something that has been known for decades but never stops being astonishing: the sheer scale of the cosmic web. If you could somehow zoom out far enough from the universe to see its large-scale structure, if you could look at the distribution of galaxies across hundreds of millions of light-years, you would see that they are not randomly distributed. They form a web, a vast, three-dimensional network of filaments and sheets, with galaxies concentrated along the filaments, galaxy clusters gathered at the nodes where filaments intersect, and enormous voids, regions hundreds of millions of light-years across where almost no galaxies exist, filling the spaces between. This structure, the cosmic web, is the largest structure in the universe, and it formed from tiny quantum fluctuations in the density of the early universe. In the first fraction of a second after the Big Bang, during or after inflation, quantum mechanics introduced tiny variations in the density of the universe, some regions slightly denser than average, some slightly less dense. Over billions of years, gravity amplified these tiny variations. Slightly denser regions attracted more matter, becoming denser still, eventually forming the filaments and clusters of the cosmic web. Slightly less dense regions lost matter to their denser neighbors, becoming voids. The entire cosmic web, every galaxy cluster, every filament, every void, is essentially a map of quantum fluctuations from the first moments of the universe, blown up to cosmic scale by 13.8 billion years of gravitational amplification. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a concentration of galaxies about 10 billion light-years across. To put that in perspective, the observable universe is about 93 billion light-years in diameter. This single structure spans roughly 10% of the observable universe. It is so large that, strictly speaking, it challenges some cosmological models. Our standard model of the universe predicts that structures above a certain size should not form, because the universe hasn't had enough time to build them. The Hercules Corona Borealis Great Wall may be close to or beyond that theoretical limit. Either the structure is not as coherent as it appears, perhaps the apparent concentration of galaxies is a projection effect or a statistical artifact, or there is something about the formation of large-scale structure that our current models don't fully capture. Let's turn now to something that involves us more personally: the fate of our own planet and our own solar system. Not the abstract heat death of the universe in 10 to the 100th years, but the specific, concrete, scheduled events that will affect the Earth on timescales of billions of years. The sun is getting brighter. Not noticeably, on a human timescale, the change is too slow for any individual or even any civilization to perceive directly. But over geological timescales, the sun's luminosity has been increasing steadily as its hydrogen fuel is converted to helium and the core slowly contracts and heats up. The sun today is roughly 30% brighter than it was when the Earth formed 4.5 billion years ago, and it will continue brightening. In roughly a billion years, the sun will be about 10% brighter than it is today, and that extra energy will likely be enough to push Earth's surface temperatures beyond what most complex life can tolerate. The oceans will begin to evaporate. The water vapor will enter the atmosphere and trigger a runaway greenhouse effect. Earth will become Venus, a scorching, airless, waterless hell. Life might persist in certain niches for longer, but the era of surface life on Earth is, on a billion-year timescale, approaching its end. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin the process of dying. It will expand into a red giant, puffing out to a size that could engulf the inner planets, possibly including Earth. Whether Earth survives the sun's red giant phase or is consumed by it depends on details of the sun's mass loss during the expansion that are not fully pinned down. If Earth's orbit expands fast enough as the sun loses mass, it might survive outside the red giant's envelope. If not, it gets incorporated into the outer atmosphere of the expanding star and spirals inward, eventually vaporizing completely. Either way, by the time the sun collapses into a white dwarf, Earth as we know it, with its oceans and atmosphere and history of life, will be gone. And in a few billion years before any of that, something else is scheduled to happen that will dramatically reshape everything. The Andromeda Galaxy, the large spiral galaxy currently about 2.5 million light-years away, is heading toward us. It's been moving toward us for a long time. It's actually the closest large galaxy to the Milky Way, and the gravitational attraction between the two galaxies is pulling them together. In about 4.5 billion years, the Milky Way and Andromeda will collide and begin the process of merging. Not a catastrophic, violent collision of stars against stars. The distances between individual stars are so vast that actual stellar collisions will be extraordinarily rare, even as the galaxies pass through each other. But the collision will disrupt the orbits of billions of stars, creating trails and bridges of stars called tidal streams, reshaping the spiral arms, triggering waves of new star formation as gas clouds are compressed by the merger dynamics, and over billions of years gradually producing a single, large elliptical galaxy from the two spirals. The merged galaxy has already been given a name, Milkomeda. What happens to our solar system during this merger is uncertain. Our sun and its planets might be flung into a very different region of the resulting galaxy. We might end up in the outer halo of Milkomeda, far from its center, in a quieter and less crowded environment than the current galactic disk. Or we might end up close to the center, in a much denser stellar environment with more radiation and a higher rate of stellar close encounters. We don't know, because the exact trajectory of our solar system through the merger depends on details of its current orbit and the dynamics of the collision that are not fully determined. But the night sky in about 4 billion years will look radically different. The familiar band of the Milky Way will be gone, replaced by a chaotic spray of stars in every direction as the two galaxies mix together. Now let's talk about something that is simultaneously beautiful and deeply strange: the physics of white dwarfs and their long, slow death. When the sun exhausts its nuclear fuel and sheds its outer layers as a planetary nebula, one of the most spectacular events in stellar evolution, the outer atmosphere of a dying star expanding into space as a colorful, intricate shell of ionized gas, what remains at the center will be a white dwarf. A white dwarf is the exposed core of the dead star, roughly the size of Earth but containing about 60% of the Sun's mass. Its density is extraordinary, about 1,000,000 times that of water, and it glows with residual heat, initially white-hot, gradually cooling over billions of years as it radiates its energy into space. White dwarfs are supported against gravitational collapse not by nuclear fusion but by something called electron degeneracy pressure, a quantum mechanical effect in which electrons resist being compressed into the same quantum states. This is the same principle that ultimately prevents atoms from collapsing. Electrons in an atom can't all be in the ground state at the same time because of the Pauli exclusion principle, which forbids two fermions from occupying identical quantum states. In a white dwarf, this principle, applied to a vast number of electrons, generates a pressure that can support the star's weight indefinitely. White dwarfs don't need to burn fuel to stay supported. They simply cool, over an unimaginably long time, gradually fading from white to yellow to orange to red to infrared to invisible. The cooling timescale for a white dwarf to fade to darkness is longer than the current age of the universe. The oldest white dwarfs we can currently detect are still glowing faintly, having not yet had time to cool completely. The universe is not old enough yet to have produced a single fully cooled black dwarf. They're a future object, something the universe will make but hasn't gotten around to yet. Let's talk about the cosmic microwave background in more detail, because there are mysteries hidden in it that are still being worked out. The CMB, as we discussed, is the afterglow of the Big Bang, the oldest light we can detect, emitted when the universe was 380,000 years old. Its temperature variations, the tiny fluctuations of 1 part in 100,000, carry an enormous amount of information about the early universe. By analyzing the pattern of these fluctuations, essentially mapping the hot and cold spots in the earliest light, cosmologists can determine the composition of the early universe, the curvature of space, the rate of expansion, and many other parameters. The CMB has been measured with extraordinary precision by a series of satellites, most recently the Planck satellite, which produced the most detailed map of the CMB ever made. And in that detailed map, there are a few features that don't fit perfectly into the standard model. One is called the CMB cold spot, an anomalously large, cold region in the southern sky that is statistically unusual. It could be explained by a supervoid, an enormous region of space with less matter than average, which would cool CMB photons passing through it through a subtle gravitational effect. But the supervoid that would be needed to explain the cold spot would be the largest known void in the universe, and observations of the region are ambiguous about whether such a void actually exists there. Another anomaly is a subtle asymmetry between the two hemispheres of the CMB. The northern and southern hemispheres of the sky appear to have slightly different temperature fluctuation patterns, which shouldn't be the case if the early universe were truly isotropic and homogeneous. And there is a feature called the axis of evil, an alignment between the largest scale features of the CMB and the plane of our solar system that has no explanation in the standard model, and might be a sign of systematic errors in the measurements, or might be pointing to something genuinely unusual about the geometry of the universe. None of these anomalies has a definitive explanation. All of them might be statistical flukes, features that arise by chance in a small fraction of universes with standard cosmological parameters, and we happen to be in one. Or they might be pointing to something real that the standard model is missing. The answer is not yet known. Let's take a moment to talk about something that sounds almost mundane by comparison, but is actually one of the most important and mysterious facts in physics: matter and antimatter. When particles of matter are created in high-energy processes, in particle colliders in the early universe, they are always created in pairs, one particle and one antiparticle, an electron and a positron, a quark and an antiquark. The laws of particle physics, as far as we can tell, are almost perfectly symmetric between matter and antimatter. Almost. There is a tiny asymmetry, a small but measurable difference in the decay rates of certain particles that causes them to behave very slightly differently from their antimatter counterparts. This asymmetry is real, it's been measured, it's called CP violation, and it's one of the conditions required, as laid out by the physicist Andrei Sakharov in 1967, for the universe to contain more matter than antimatter. Which is good, because the universe does contain more matter than antimatter. We're made of matter. Everything we can see is made of matter. The observable universe contains essentially no large-scale concentrations of antimatter. This is enormously fortunate, because matter and antimatter annihilate each other on contact. When a particle and its antiparticle meet, they destroy each other and convert their combined mass into energy. If the universe had started out with exactly equal amounts of matter and antimatter, as the symmetric laws of physics might suggest it should, they would have annihilated each other completely in the first moments after the Big Bang, leaving nothing but radiation. No matter, no atoms, no stars, no planets, no us. The fact that there's a slight imbalance, roughly one extra matter particle for every billion matter-antimatter pairs, is what allowed the universe to survive its own infancy. After all the annihilation, that tiny excess of matter was what was left. And from that small remainder, everything in the observable universe was built. The ratio of photons to protons in the universe today, roughly 1 billion photons for every proton, is the fossilized remnant of that almost perfect cancellation. Every atom in your body, every molecule of water in the oceans, every star in every galaxy, exists because of a 1 in a billion asymmetry in the laws of physics that we do not yet fully understand. The amount of CP violation that has been measured in experiments, the degree of asymmetry between matter and antimatter particles, is not large enough to account for the observed matter-antimatter asymmetry of the universe. The standard model of particle physics, even with all the CP violation it allows for, cannot explain why we're here. There must be additional sources of CP violation that we haven't found yet, new physics beyond the standard model that breaks the matter-antimatter symmetry more strongly than anything we've currently discovered. Finding that new source of symmetry breaking is one of the great open challenges of particle physics, because it is literally the question of why the universe contains anything at all. Now let's talk about something that's genuinely difficult to conceptualize but is one of the most experimentally well-confirmed aspects of quantum mechanics: quantum entanglement. Einstein famously called it spooky action at a distance, and his discomfort with it led him to propose that there must be some undiscovered hidden variable, some underlying reality that would explain it away. He was wrong. Experiments have now confirmed, beyond any reasonable doubt, that quantum entanglement is real and that it works exactly the way the theory predicts, with no hidden variables required. Here's what entanglement is. Two particles can be prepared in a state where their quantum properties are correlated. The quantum states of the two particles are intertwined in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. If you measure the spin of one particle and find it pointing up, the spin of its entangled partner will be found pointing down, instantly, regardless of whether the particles are across the room or across the galaxy. Not almost instantly, not at the speed of light. Instantly, the correlation is established the moment you make the measurement, with no signal traveling between the particles. This seems to violate special relativity's prohibition on faster-than-light communication. But it doesn't, quite, because you can't use entanglement to send information. The result you get when you measure your particle is random. You can't choose whether to get spin up or spin down. You just get a random outcome. The fact that your partner gets the correlated outcome doesn't help them, because they also got a random outcome, and without you calling them on the phone, at the speed of light or slower, to tell them what you measured, they have no way of knowing whether their result is correlated with yours or not. Entanglement creates correlations but doesn't transmit information, and that's what saves the consistency of special relativity. But the correlations are real. They cannot be explained by any local hidden variable theory. The universe really does have these non-local correlations built into it at the quantum level, and what that means for our understanding of the nature of space and causality is something physicists are still working out. Quantum mechanics as a whole, the theory that describes the behavior of matter and energy at the smallest scales, is arguably the most successful scientific theory ever devised. Its predictions have been confirmed to a precision of 1 part in a trillion in some cases. The technology of the modern world, transistors, lasers, MRI machines, the entire semiconductor industry, is fundamentally based on quantum mechanical principles. And yet what quantum mechanics means, what it tells us about the nature of reality, is almost entirely unclear. The theory predicts measurement outcomes with extraordinary accuracy, but it doesn't tell us a coherent story about what is actually happening between measurements. Particles don't have definite positions or momenta until they're measured. The act of measurement somehow collapses a wave of probability into a single definite outcome. Whether this collapse is a real physical process or just an update of our knowledge, whether the many worlds interpretation is correct and every measurement branches reality into multiple worlds where each possible outcome occurs, whether there is some deeper theory that will make quantum mechanics more intuitively sensible, these questions are not just unanswered but are among the most actively debated questions in all of physics and philosophy. Let's talk about the life cycles of stars more broadly, because stellar evolution contains some of the most extraordinary and poignant stories in nature. Stars form from clouds of gas and dust, nebulae, that collapse under their own gravity when they reach sufficient density. The collapse heats the gas, and if enough mass is present, the temperature and pressure at the center reach the point where hydrogen fusion begins, and a star is born. The mass of the star determines almost everything about its life: how hot it burns, how long it lives, what it becomes when it dies. The most massive stars, those more than about 8 times the mass of the Sun, burn brilliantly and briefly, measured in millions rather than billions of years. They exhaust their fuel in what is, by stellar standards, an almost indecent hurry, blazing so brightly that they can be seen from other galaxies, and then dying in the core collapse supernovae we discussed earlier. The elements they synthesize in their interiors and scatter in their explosions, the carbon, oxygen, nitrogen, silicon, iron, and all the heavier elements up to and beyond, are the raw material of the universe's chemistry. Your carbon was forged in the interior of a star that died before the sun was born. The iron in your blood was produced in the explosion of a star whose death scattered it into the interstellar medium, from which the solar nebula formed 4.5 billion years ago. You are made of dead stars, not metaphorically. Literally. Every heavy atom in your body was created by stellar nucleosynthesis in a star that no longer exists. Medium-mass stars like our Sun live for billions of years in the stable hydrogen-burning phase, eventually expanding into red giants, shedding their outer layers as planetary nebulae, and leaving white dwarfs. The planetary nebulae they produce are among the most beautiful objects in the sky. Intricate, colorful shells of glowing gas, shaped by magnetic fields and stellar winds and the rotation of the dying star into forms that range from simple spherical bubbles to complex hourglass shapes to elaborate spirals with multiple shells. The Ring Nebula in Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco. These are the death shrouds of stars not unlike our Sun, the outer atmospheres they shed as they died, glowing with the energy of the hot white dwarf remnant at the center. And the least massive stars, the red dwarfs, the M-type stars that make up more than 70% of all stars in the galaxy, burn so slowly and so coolly that they can live for trillions of years. The universe at 13.8 billion years old is nowhere near old enough for even the oldest red dwarfs to have died. They are still burning, still fusing hydrogen, still hosting any planets they might have, as patient and persistent as anything in the universe knows how to be. A red dwarf star born at the same time as the universe will still be burning when the universe is 100 times its current age. Whatever worlds orbit those stars have had trillions of years to develop whatever they might develop. We have no idea what a world looks like after a trillion years of uninterrupted existence. Let's shift gears entirely and talk about something much closer to home that doesn't get nearly the attention it deserves: the deep interior of the Earth, and what it tells us about the violence that built the world we live on. The Earth is not a peaceful place. Its surface gives the impression of solidity and stability. The ground beneath your feet feels like the most reliable thing in the world, and mostly it is, on a human timescale. But beneath that surface, the Earth is in continuous violent motion. The outer core of the Earth, the layer between roughly 2,900 and 5,150 kilometers depth, is liquid iron and nickel, flowing in complex patterns driven by the heat from the inner core and from radioactive decay in the surrounding rock. This flowing, electrically conductive iron is what generates Earth's magnetic field, the geodynamo, the process by which the kinetic energy of the flowing metal is converted into the magnetic field that surrounds the planet and shields the surface from the solar wind and cosmic radiation. Without the geodynamo, Earth's magnetic field would disappear, and the consequences would be severe. The solar wind, the stream of charged particles constantly blowing outward from the sun, would slowly but relentlessly strip away Earth's atmosphere over millions of years, the same process that is thought to have stripped Mars of most of its atmosphere after Mars's own geodynamo shut down billions of years ago. The radiation environment at Earth's surface would also change dramatically, with more cosmic rays and solar energetic particles reaching the ground and causing higher rates of DNA damage and mutation. Life would adapt, presumably. Life has survived worse. But the Earth without its magnetic field would be a fundamentally different planet. The Earth's magnetic field is not stable. It reverses polarity on irregular intervals, averaging perhaps once every few 100,000 years, though the most recent reversal was about 780,000 years ago, and we may be due for another. During a reversal, the field doesn't simply flip from pointing north to pointing south overnight. It gradually weakens, becomes increasingly chaotic and irregular, with multiple magnetic poles appearing in various locations around the globe, and then over a period of thousands of years gradually reorganizes and strengthens in the opposite orientation. During this transition, the magnetic shielding is reduced, potentially exposing the surface to higher levels of radiation. Whether past reversals have been associated with mass extinctions or other biological disruptions is debated. The evidence is ambiguous. But the fact that we are currently in a relatively long interval between reversals, and that the magnetic field has been weakening at a measurable rate over the past century and a half, is at minimum an interesting thing to keep track of. The tectonic plates that make up Earth's crust are themselves the expression of an extraordinary geological process driven by the heat of the interior. The convection of the mantle, the slow, gradual flow of solid rock over millions of years, behaving like a viscous fluid on geological timescales, carries the plates on its surface, driving them together, pulling them apart, shoving them sideways past each other. Where plates converge, one can be driven beneath the other in a subduction zone, carrying oceanic crust deep into the mantle where it melts, generating volcanism at the surface above. Where plates diverge, molten rock wells up from below to fill the gap, creating new crust. Where plates slide past each other, the accumulated stress is periodically released in earthquakes. This system of plate tectonics is not just geologically interesting. It is, many scientists believe, one of the reasons complex life exists on Earth. Plate tectonics drives a long-term carbon cycle that regulates Earth's climate on geological timescales, keeping the planet from freezing into a snowball or overheating into a runaway greenhouse. Volcanoes release carbon dioxide into the atmosphere, warming the planet. When continents weather, when rain falls on exposed rock and breaks it down chemically, carbon dioxide is drawn out of the atmosphere and eventually carried to the ocean and buried in sediments. As sediments are subducted, the carbon is returned to the interior, completing the cycle. This thermostat operates on time scales of hundreds of millions of years, and it has kept Earth habitable, warm enough for liquid water, cool enough for life, for most of its 4.5 billion year history. Mars and Venus appear to lack active plate tectonics, and both are, in their different ways, uninhabitable. Whether Earth's unusually active tectonic system is a coincidence or a prerequisite for life is one of the more interesting questions in astrobiology. Now let's talk about water. Water seems simple, just two hydrogen atoms and an oxygen atom, the simplest and most common molecule in the universe after molecular hydrogen and carbon monoxide. But water has a set of physical and chemical properties so unusual, so seemingly tailored for the support of life, that it has been discussed by biologists and chemists for generations as one of the most remarkable substances in nature. It's less dense as a solid than as a liquid. Most substances are denser in their solid form than in their liquid form, but ice floats on water. This single anomalous property has enormous biological consequences. It means that when a body of water freezes, it freezes from the top down, and the ice forms an insulating layer that protects the liquid water below. Ponds and lakes and rivers stay liquid under their ice, allowing aquatic life to survive winters that would otherwise freeze everything solid. Water has an extraordinarily high heat capacity. It resists changes in temperature more than almost any other common substance, which is why the oceans moderate Earth's climate so effectively, absorbing heat in summer and releasing it in winter. It has a high surface tension, enabling the biological processes that depend on water being pulled up through narrow tubes against gravity, capillary action, which drives water from the roots to the leaves of trees, from the base to the tops of the largest organisms that have ever lived. It is an almost universal solvent, capable of dissolving an enormous range of substances, which makes it the ideal medium for the chemical reactions of life. Its transparency to visible light allows photosynthesis to occur deep in the water column. Its high latent heat of evaporation makes it an effective coolant for the bodies of organisms that need to regulate their temperature. If you were designing a solvent for life from first principles, you would have a very hard time doing better than water, and water is extraordinarily common in the universe. Oxygen and hydrogen are the first and third most abundant elements in the cosmos, and water molecules form readily wherever they have the chance. The universe is full of water, much of it in the form of ice in comets and asteroids, in the cold regions of interstellar space, on the surfaces of moons far from their stars. Wherever liquid water exists in the universe, wherever the conditions are right for it to be liquid rather than ice or vapor, the ingredients for life as we understand it are present. That is the logic behind the search for liquid water as a proxy for the search for life, and it is why the discovery of evidence for liquid water on Mars, in the subsurface oceans of Europa and Enceladus, in the methane lakes of Titan, and in the atmospheres of exoplanets feels so significant. Europa, one of the 4 large moons of Jupiter, deserves special attention here because it is one of the most compelling candidates for extraterrestrial life in our own solar system. Europa is slightly smaller than Earth's moon and is covered in a smooth shell of ice, the smoothest surface in the solar system, with almost no impact craters, suggesting that the ice is being continuously renewed by geological activity from below. Beneath that ice, the tidal flexing of Europa's interior by Jupiter's enormous gravitational field generates enough heat to maintain a global liquid water ocean with an estimated depth of up to 100 kilometers, far deeper than any ocean on Earth. The total volume of water in Europa's subsurface ocean is estimated to be roughly twice the total volume of all water on Earth's surface. This ocean is in contact with a rocky seafloor, where hydrothermal venting may be occurring, the same process that drives the deep-sea vent ecosystems on Earth that are among the most biologically productive and diverse environments on our planet. Europa's ocean has been in contact with its rocky seafloor for potentially billions of years. It has liquid water, chemical energy from hydrothermal vents, and possibly organic compounds delivered by comets and asteroids. These are the same ingredients that many researchers believe led to the origin of life on Earth. Whether life has actually arisen in Europa's hidden ocean, we don't know. NASA's Europa Clipper mission is on its way to the Jupiter system to study Europa in more detail, though it won't land or drill through the ice to sample the ocean directly. That mission, if it ever flies, is still in the future. But the scientific consensus is that Europa is one of the most promising places in the solar system to look for life, and that its existence as a potentially habitable world, hidden beneath 10 to 30 kilometers of ice, in a dark ocean never touched by sunlight, expands our sense of where life can be in ways that go far beyond our own planet. Let's talk about the origin of the moon, because it is one of the most dramatic events in Earth's history, and because the story of how the moon formed is in its own way one of the most remarkable geological detective stories ever told. The leading theory, the giant impact hypothesis, proposes that early in Earth's history, about 4.5 billion years ago, when the solar system was still young and the inner planets were still being shaped by frequent large impacts, a body roughly the size of Mars struck the proto-Earth in a glancing collision. This impactor, called Theia, was destroyed in the impact, and its material mixed with the outer layers of the proto-Earth. The collision released an enormous amount of energy, enough to vaporize the impactor entirely, and blast a significant portion of Earth's outer layers into orbit. That orbiting cloud of vaporized rock gradually cooled and coalesced into the moon we have today. The evidence for this theory is compelling. The moon has a composition that closely matches Earth's mantle, suggesting they formed from the same material. The moon is almost entirely lacking in volatile elements, substances that evaporate easily, which is consistent with a formation event involving enormous heat. The moon has a relatively small iron core compared to its size, which is consistent with its forming primarily from the silicate-rich outer layers of both Earth and Theia, rather than from their iron cores, which would have already sunk to the centers of both bodies before the impact. The angular momentum of the Earth-Moon system, the way the two bodies orbit each other and how that orbit relates to Earth's rotation, is also consistent with the giant impact scenario. But recent analysis of the moon's composition has revealed something puzzling. The moon's isotopic composition, the specific ratios of different isotopes of elements like oxygen and tungsten, is extraordinarily similar to Earth's, far more similar than you'd expect if a significant portion of the moon's material came from Theia, which should have had a different isotopic signature from Earth. Either Theia happened to have the same isotopic composition as Earth, possible but unlikely, or the impact was more violent and the mixing of Earth and Theia material more complete than previous models suggested, possible but requiring models to be revised, or the moon formed from a different kind of impact than the standard model proposes. Several alternative scenarios have been explored, including a more energetic collision that vaporized both bodies into a rapidly rotating cloud of magma vapor that eventually coalesced, but the details are still being worked out. The moon is also slowly moving away from Earth. Tidal friction is gradually slowing Earth's rotation, and by the conservation of angular momentum, transferring that rotational energy to the moon's orbit, causing it to slowly spiral outward. The moon is currently moving away from Earth at a rate of about 3.8 centimeters per year, roughly the same rate at which your fingernails grow. We know this with extraordinary precision because Apollo astronauts placed laser reflectors on the lunar surface, and we have been bouncing laser pulses off them for decades, measuring the round-trip time to determine the moon's distance with millimeter accuracy. Over billions of years, this gradual recession means that the moon will eventually be far enough away that total solar eclipses, currently possible because the moon is almost exactly the right size to just cover the sun's disk, will no longer occur. We live in a very specific window of Earth's history when total solar eclipses are possible, and future inhabitants of Earth, if there are any, billions of years from now, will not see them. Let's talk about something that doesn't get enough attention in popular space content: the interstellar medium. The space between stars is not empty. It is filled with a thin but real mixture of gas and dust, hydrogen in both atomic and molecular forms, helium, traces of heavier elements, small dust particles composed of silicate and carbon compounds with icy mantles. This material, the interstellar medium, is the raw material from which new stars and planets form. It is also the graveyard of dead stars. The processed material returned to space by supernovae and stellar winds mingles with the primordial hydrogen and becomes the feedstock for the next generation of stellar birth. The structure of the interstellar medium is complex and turbulent. It consists of several distinct phases at radically different temperatures and densities, existing in rough pressure equilibrium with each other. Hot, diffuse gas at temperatures of millions of degrees fills the bubbles carved out by supernova explosions. Warm gas at thousands of degrees fills the general interstellar volume. Cold, dense clouds at tens of degrees form the sites of star formation. Within these cold clouds, where the density is high enough to shield the interior from the ultraviolet radiation that would otherwise destroy molecules, an extraordinarily rich chemistry occurs. More than 200 different molecules have been detected in interstellar space, including water, ammonia, formaldehyde, ethanol, and complex organic molecules like amino acid precursors. The building blocks of life are distributed throughout the interstellar medium, raining down on newly forming planetary systems in the form of dust and ice. This means that when Earth formed 4.5 billion years ago, it was immersed in an environment already rich in organic chemistry, and the delivery of organic compounds to the early Earth by comets and asteroids and the capture of interstellar dust was not an exotic process, but a normal, expected feature of planetary formation. This has profound implications for the origin of life, because one of the great obstacles in explaining how life started is explaining how the complex organic molecules necessary for biology, amino acids, nucleotides, Lipids could have formed on the early Earth before life existed to make them. The discovery that many of these molecules form naturally in the interstellar medium and in comets and asteroids, and that the early Earth was constantly being seeded with them from space, suggests that the raw materials for life were not just available but abundant. The question shifts from where did the building blocks come from to how did they assemble themselves into the first self-replicating system, which is still a profound and unanswered question, but a different and perhaps more tractable one. Let's talk about neutron star mergers in more detail, because in 2017 something happened that was one of the most extraordinary moments in the history of observational astronomy. On August 17, 2017, gravitational wave detectors in the United States and Europe detected a gravitational wave signal from the merger of two neutron stars about 130 million light-years away. This was the first neutron star merger ever detected through gravitational waves, and it was also the first gravitational wave source to have a confirmed electromagnetic counterpart, meaning that 1.7 seconds after the gravitational wave signal arrived, a burst of gamma rays from the same location was detected by a space telescope. In the days and weeks that followed, the merger was observed across the entire electromagnetic spectrum, from radio waves to X-rays, by dozens of telescopes around the world and in space. What they saw was a kilonova, the brilliant, rapidly fading glow produced by the collision and merger of two neutron stars. The kilonova was powered by the radioactive decay of heavy elements synthesized in the merger, elements heavier than iron, produced by a process called rapid neutron capture, or the R process, in which atomic nuclei capture neutrons so rapidly that they build up far heavier elements than normal stellar fusion can produce. In the spectrum of the kilonova, astronomers detected the signatures of gold, platinum, strontium, and other heavy elements produced in real time by the merger. That event, 130 million light-years away, produced more gold than 10 times the mass of the Earth. Neutron star mergers are the primary cosmic factory for the universe's heavy elements. The gold in your jewelry was made in a neutron star collision billions of years ago, scattered into space, incorporated into the cloud from which the solar system formed, and eventually concentrated on Earth by geological processes. Every piece of gold that has ever been mined, worn, traded, or admired has a history that begins with two neutron stars spiraling together and annihilating each other in a flash of light so bright it could be seen 130 million light-years away. The gravitational wave detection of that merger was itself extraordinary. Gravitational waves are ripples in spacetime, distortions in the fabric of space itself, produced by accelerating masses, and they were predicted by Einstein's general theory of relativity in 1916. Einstein himself doubted they'd ever be directly detected because the effect they produce, a stretching and squeezing of space itself as the wave passes, is so incredibly small. The first gravitational wave detection in September 2015 was of two black holes merging about 1.3 billion light-years away, and the signal it produced was a distortion of space of about 10 to the minus 21 meters, 1,000th of the diameter of a proton. Detecting a signal that small required an instrument that measures the length of a 4-kilometer arm to a precision of 1/10,000th of the diameter of a proton. LIGO, the Laser Interferometer Gravitational Wave Observatory, is not just the most sensitive measuring instrument ever built. It is arguably the most extraordinary piece of technology our civilization has produced, and it has opened an entirely new way of observing the universe. A new kind of astronomy that sees not light but the warping of spacetime itself. A new messenger from the universe, one that can pass through matter without interaction, one that cannot be blocked or scattered or absorbed, carrying information about the most violent events in the cosmos from virtually any distance. Let's talk about the Fermi paradox more carefully, because it's one of the most important and least satisfying puzzles in all of science, and there's more to it than the simple version usually presented. The setup is familiar. The galaxy is roughly 13 billion years old, far older than our Sun and Earth. There are hundreds of billions of stars, and we now know that most of them have planets, and that a significant fraction of those planets are in roughly the right range for liquid water. Even if the probability of intelligent life developing on any given habitable planet is very small, 1 in a million, say, or 1 in a billion, the sheer number of chances means that, by almost any reasonable estimate, intelligent life should have arisen many times in the galaxy's history. And if even one of those civilizations developed the ability and motivation to spread through the galaxy, And if travel or communication across interstellar distances is possible in any timescale that's short compared to the age of the galaxy, then the galaxy should be full of evidence of intelligence. Yet we see nothing. The proposed resolutions to the Fermi paradox are many and varied, and most of them are disturbing in some way. One class of explanation says that the paradox is dissolved by recognizing that we haven't actually looked very hard. Our SETI programs have been underfunded and limited in scope. We've only studied a small fraction of possible signal types and frequencies, and absence of evidence is not evidence of absence. Another class says that interstellar travel or communication is much harder than we assume, and that even motivated civilizations find it impractical to spread across the galaxy. Another says that intelligent life is far rarer than we assume, that the steps leading from simple chemistry to self-replicating molecules, or from single-celled life to multicellular organisms, or from animals to tool-using intelligence, are individually so improbable that they almost never all occur on the same planet. And then there's the Great Filter, the idea, proposed by economist Robin Hanson, that there is some barrier, some filter, in the development of civilizations that almost all potential civilizations fail to pass. The Great Filter is something, we don't know what, that explains why the galaxy isn't teeming with detectable intelligence. The critical question is where in the developmental sequence the Great Filter lies. If it's behind us, if it's something in the early stages of life's development, something that makes getting from chemistry to intelligent organisms enormously difficult, then we've already passed it, and the fact that we exist is an enormous stroke of luck, but there's no reason to fear that something catastrophic lies ahead. If the Great Filter is ahead of us, if it's something that advanced civilizations inevitably encounter that destroys them, like their own technology, or a universal tendency to collapse, or some cosmic threat we haven't yet recognized, then our future is deeply uncertain, and the silence of the galaxy is a warning rather than a lucky circumstance. The discovery of simple life on another planet would be among the most terrifying things that could happen, from a Great Filter perspective. Because if simple life is common, if microbial life arises readily wherever conditions are right, then the Great Filter is almost certainly not the origin of life. It must lie somewhere between simple life and advanced civilization. And if it's ahead of us, then the silence of the galaxy might be because every civilization that has reached our stage has been destroyed by something that we will also inevitably encounter. The cheerful discovery of bacteria on Mars might be the worst news in history. Let's turn from the philosophical to the visceral and talk about some of the specific cosmic threats that exist and what they mean for our long-term future. We've talked about gamma-ray bursts. Let's talk about something called the Magnetar SGR 180620, because it illustrates something important about how dangerous the universe can be from very large distances. In December 2004, SGR 180620, a magnetar in our galaxy about 50,000 light-years away, produced the most energetic event ever observed from beyond our solar system. The burst lasted about 0.2 seconds. In those 0.2 seconds, it released more energy than the Sun emits in 250,000 years. The burst was bright enough to ionize Earth's upper atmosphere, an effect normally produced only by our own Sun, from 50,000 light-years away. It caused measurable changes in the ionosphere. It was detected by spacecraft designed to study gamma-ray bursts from other galaxies, and it saturated their detectors because it was so much brighter than extragalactic sources that the instruments weren't designed for it. If SGR 1806 were 10 light-years from Earth instead of 50,000, the burst would have been comparable in energy to a nuclear weapon detonating in our upper atmosphere. If it were within about 3,000 light-years and oriented with its beam pointing toward us, it could have stripped the ozone layer. This is a real object. It is in our galaxy, and events like this happen somewhere in the universe regularly. The universe is full of similar violent objects. There are at least a dozen known magnetars in the Milky Way. There are countless neutron stars. There are hundreds of millions of stellar mass black holes. There are supernova candidates within a few thousand light-years. There are the dense regions of the galactic center, where stellar density and radiation intensity are thousands of times higher than in our neighborhood. The solar system sits in a relatively quiet, relatively safe corner of the galaxy, far from the center, far from the most active star-forming regions, in a neighborhood where stellar density is moderate and radiation hazards are manageable. Whether this is coincidence or whether life requires such a safe neighborhood to develop is something astrobiologists call the galactic habitable zone hypothesis. The idea that only certain regions of a galaxy are truly safe and hospitable for the development of complex life, and that the solar system's location in one of those regions is part of why we're here. Let's talk about one of the most strange and profound discoveries in the history of cosmology. In 1965, two engineers at Bell Labs named Arno Penzias and Robert Wilson were calibrating a radio antenna and kept picking up a persistent, annoying background hiss in the microwave frequency range. It was coming from every direction in the sky with equal intensity. They couldn't explain it. They tried to get rid of it. They even cleaned pigeon droppings out of the antenna in case that was the cause. The hiss remained. A few miles away, a group of cosmologists were working on the theoretical predictions of the Big Bang model, which predicted exactly this kind of microwave background radiation as the relic of the early universe. When they learned of Penzias and Wilson's anomalous signal, they immediately recognized what it was. The engineers had accidentally discovered the cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang, a discovery so significant that it effectively confirmed the Big Bang model as the correct description of the universe's origin, and earned Penzias and Wilson the Nobel Prize in Physics in 1978. The story of the cosmic microwave background discovery has always struck me as one of the most extraordinary cases of scientific serendipity in history. The most ancient and important piece of radiation in the universe, the signal that carried information about the first moments of creation, was discovered because two engineers couldn't figure out why their antenna was making an annoying noise. The universe was trying to tell them something, and they kept trying to tune it out. When they finally stopped fighting it and started listening, they heard the Big Bang. Let's talk about black hole thermodynamics, because it's one of the most extraordinary intersections of seemingly unrelated areas of physics, and because the ideas at the center of it, developed primarily by Stephen Hawking in the 1970s, are among the most profound and puzzling in all of theoretical physics. Hawking showed, using a combination of quantum mechanics and general relativity, that black holes are not entirely black. They emit radiation, not from within the event horizon where nothing can escape, but from the event horizon itself through a quantum mechanical effect. Pairs of virtual particles, particle and antiparticle pairs that quantum mechanics allows to temporarily appear from nothing before annihilating, can appear near the event horizon in such a way that one particle falls in while the other escapes. The escaping particle takes energy away from the black hole, which means the black hole loses mass. It evaporates over an incomprehensibly long time, longer for more massive black holes. Any black hole will eventually radiate away all its mass and disappear in a final burst of Hawking radiation. Speaking of wormholes, let's talk about wormholes, because they are predicted by general relativity. They are not physically forbidden by current theory, and yet they present problems so severe that their existence in any useful form seems deeply unlikely, while their non-existence is also not proven. A wormhole, technically an Einstein-Rosen bridge, is a solution to Einstein's field equations in which two distant regions of spacetime are connected by a tunnel. In principle, you could enter a wormhole at one point in space and exit at another point light-years away, having traveled a distance much shorter than the direct path through ordinary space. In principle, if the wormhole connected two regions at different times, it might even allow travel to the past, with all the paradoxes that entails. The problems with wormholes are substantial. First, any wormhole solution to Einstein's equations requires exotic matter, matter with negative energy density, to hold the throat of the wormhole open against gravitational collapse. No such matter is known to exist in the quantities required. Certain quantum effects can produce regions of negative energy density, but whether they could be deployed to stabilize a macroscopic wormhole is deeply uncertain. Second, even if a stable wormhole could be created, the quantum mechanical analysis suggests that any attempt to send information through it would be met with a flood of radiation that would destroy the wormhole before the information arrived. Third, if wormholes allowed time travel, they would permit the grandfather paradox, going back in time to prevent your own birth. And most physicists believe that some mechanism, possibly quantum mechanical, would prevent this from happening even in a universe where wormholes existed. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel, even in situations where it seems geometrically possible, as a way of protecting the consistency of causality. Whether the universe contains wormholes, whether they can be created, whether they could ever be traversable, whether time travel is possible. All of these are genuinely open questions. They're not science fiction, their theoretical physics, and the fact that the answer to all of them is genuinely unknown, that our best theories of physics cannot definitively rule out wormholes and time travel, says something remarkable about how much we don't yet understand about the structure of reality. Let's end this section by talking about something that cuts across all the categories we've explored, something that is simultaneously one of the most beautiful and one of the most unsettling facts about the universe. It's the fact of emergence. In a universe governed by the laws of physics, laws that describe the behavior of particles and fields, that are mathematical and precise and impersonal, from those simple cold rules, the universe has produced extraordinary complexity. It has produced stars that synthesize new elements in their cores. It has produced planets with complex geology, chemistry, and weather. It has produced self-replicating molecules. It has produced life. It has produced organisms with brains capable of representing models of the external world. It has produced consciousness, whatever that is, and we genuinely don't know what it is. The subjective experience of being a creature in the world, the sense of what it feels like to see red or to feel pain or to contemplate the Milky Way on a clear night. How does consciousness arise from matter? How does subjective experience emerge from the electrochemical activity of neurons? This is called the hard problem of consciousness, and it is genuinely one of the most difficult questions in all of science and philosophy, distinct from and much harder than the relatively tractable questions of how the brain processes information and produces behavior. We can map the neural correlates of conscious experience. We can identify which brain regions are active when we experience pain or joy or recognition, but we cannot explain why there is any subjective experience at all, why the processing of information in a neural network should feel like anything from the inside, why it isn't all just dark, mechanical information processing with nobody home. Some philosophers argue that consciousness is a fundamental feature of the universe, not emergent from matter but built into it at some level, perhaps all the way down to the most basic physical processes. Others argue that it's an emergent property of sufficiently complex information processing systems, and that the hard problem will eventually dissolve when we understand information processing well enough. Others argue that consciousness might be multiple different things, that what we call consciousness is actually a cluster of different phenomena, some of which are more tractable than others, and that the hard problem as traditionally stated may be confused. Nobody has a convincing answer, and the question matters not just philosophically but practically, because it bears on questions of which systems deserve moral consideration, how we should think about artificial intelligence, and what it would even mean to find alien life. In a universe this vast, this old, this full of complexity, in a universe where matter has organized itself into stars and planets and oceans and cells and nervous systems and minds, the most mysterious and most important question might not be about black holes or dark matter or the fate of the cosmos. It might be about what you are. What it means that there is something it is like to be you, that somewhere in this 93 billion light-year observable universe, in this cosmos of 2 trillion galaxies and quadrillions of stars, a collection of atoms arranged into a few pounds of neural tissue can look up at the sky and ask why. That capacity, for wonder, for questioning, for the desire to understand, did not have to exist. The universe did not have to produce it. The laws of physics, tuned differently, would have given us a universe of gas and light and gravity with nobody to observe any of it, with nothing to ask or wonder or care. We are here, asking these questions, because of a nearly unbroken chain of cosmic fortunate accidents going back 13.8 billion years, from the fine-tuned constants that allowed atoms to form, to the supernovae that built the heavy elements, to the collision that made the moon, to the billions of years of biological evolution that made nervous systems capable of self-reflection. The universe is full of wonders and horrors and mysteries. It is full of objects that would destroy us without a second thought. Magnetars and gamma-ray bursts and black holes and supernovae, and the slow creep of the accelerating expansion that will eventually erase the evidence of our own existence. It is full of things we don't understand and may never understand. Dark matter and dark energy and the information paradox and the nature of consciousness and the question of why there is something rather than nothing. It is full of extraordinary beauty. The cosmic web and planetary nebulae and the fossil glow of the Big Bang and the neutron stars spinning hundreds of times a second in their lonely corners of the galaxy. And it is full of us. Or at least one of us, at least one planet, as far as we currently know, where the universe looked in a mirror and found something looking back. That might be the most extraordinary thing of all.